All right. Ladies and gentlemen, as you were coming in, I had a stack of the equation sheets. Okay, they have my name on them. They're not yours. Don't steal them. Theft is a crime. These are yours to borrow for the day because I forgot to print them off for you today, even though I promised. Sorry. Okay? What I would like for you to do, flip over to the back side of this equation sheet, and I want you to look at the top half of it. It says gases, liquids, and solutions. And I want you just to scan your eyes down these equations that are given. There's a lot of really good stuff here, okay? There's stuff there that makes it so you don't have to memorize. Also, move your eyes over to the right-hand side. You've got all these variables defined, and then you've got the ideal gas law constants given there. You've got some pressure conversions there. You're even given the conditions at STP. Right? Lots of good stuff there. This equation sheet, which I promise for real this time, to get you a copy of next class. You will get these with every test from now on, and you get them on the AP exam. Okay? So let's keep this out because there's some helpful information on here. I'll have you give them back at the end of class. Okay? But guys, just to recap the big topic that we covered last class was merging two big topics together. Gas laws and reactions in stoichiometry. We put those two big things together into one problem. Okay? You're going to get some more practice with that today with just one little added piece to it. In these word problems that you see, there is a phrase that will come up again and again and again when you have gas law stoichiometry problems. The problem will say something along the lines of, a gas was collected over water. Collected over water. That is a phrase you're going to see a lot. And I want to explain to you what that means and how that changes a word problem. So let's focus in on this picture here. What we've got here is some kind of compound that is being decomposed, and one of the products is a gas. One of the products of this decomposition is oxygen gas, O2. We're going to do a very similar kind of setup in the next lab that we do, which is, I don't know when. But what's going on here is the oxygen gas is traveling through this tube down into this bowl of water where there is an inverted jar, okay? And you may not be able to see it from where you're sitting, but there's some little bubbles, okay? And that oxygen gas is collecting up here. Okay? Now, this jar started out at the beginning of the reaction completely filled to the top with water. And then as the reaction goes on and the oxygen gas is being produced, the water level drops. And this is a really handy way to collect a gas. There is a problem, however. Let's say that I tell you that the pressure in this space is, I don't know, give me a number, throw out a number.
13.
12. All right, well, I like 13. 13. All right, that's pretty ridiculous that would be at a pressure of 13 atmospheres, but whatever. Okay. Here's the problem. If I say the pressure in this space is 13 atmospheres, that does not mean the pressure of oxygen gas is 13 atmospheres. And here's the reason why. Because I have collected this gas over water, what's in this space is not just oxygen. Okay? There is some water vapor in this space as well. Okay? And guys, you should know, if you don't know already, if you have any closed container of any liquid, in the space above that liquid, there will be some vapor of whatever your liquid is. So in my water bottle right now, sure, there's air in this space, but there is also some water vapor in that space because there is water here. So there's not one gas up here. There's two gases up here. If I need to know the pressure of just the oxygen alone, what else do I need to figure that out? Pressure of the water. Okay, so let's say in a problem I gave that to you and I said the pressure of the water vapor is 2 atmospheres. What's the pressure of just the oxygen? Please don't get a calculator out. Thank you, 11. Okay? The point is, you're going to see this situation in problems a lot. A lot. They're going to say, this gas was collected over water. If that is the case, you will need to be given the vapor pressure of the water so that you can subtract it from the total pressure. Because what you want is the pressure of just that one gas. You don't want the pressure of multiple gases. Okay? So, this problem is very much like some of the problems we did last class, bringing gas laws and stoichiometry together. Remember what I told you last class. If you see a reaction, you're going to be doing stoichiometry and a gas is involved. Do you remember what the big $1 million question was that you need to ask yourself? Do you remember? Are we at STP or not? Are we? No. Look at the pressure. Look at the temperature. We are not at STP. And ladies and gentlemen, if you are not at STP, what are you not allowed to use? 22.4. You can't use it. So what will you be using at some point? The ideal gas law. My suggestion is write out the ideal gas law because you know you're going to be using it at some point. Figure out what parts of that ideal gas law do you have, what parts are you missing. Try it. Talk it out with people around you. Okay, ladies and gentlemen, I want to sort of talk through the thought process. Because when we did a problem last class, very similar to this, where there was stoichiometry and gas laws. I got the question multiple times. How do you know where to start? Well, in my mind, let me scroll back up. Remember I told you again, you see a reaction, you see there's gas laws involved, ask yourself, are we at STP? And you said the answer was no, which is correct. So what I do when I'm trying to plot out how I want to solve this is I say, okay, I'm going to use the ideal gas law. So I write it out and I see what do I have and what do I not have. Do you agree that I was given a pressure of the gas? Or I could get it anyway? Say yes.
Yes.
Okay. I was not given a volume of the gas.
Yes.
Listen, please. Thank you. This one might have tripped some people up. Okay? There is no number of moles of anything given in the problem. But as I was walking around, I saw some people changing this value, this mass right here, into moles and plugging it in. Why is that incorrect? Meg? Okay, correct. This is an ideal gas law. This is not a gas. You can't plug in moles of a solid into the ideal gas law. So that's why there's no check mark over it. I don't know how much gas I have. We always have a value for R. I was given a temperature. Doing that little step tells me I need to start this problem by getting moles of my gas through stoichiometry. And then notice what I did. Then I said, okay, yeah, I've got the moles now. Now I can solve for the volume. Okay. Right here. Because remember, it said the gas was collected over water, which means this pressure, 94 torr, is the pressure of the space above that water. But the space above that water does not contain just oxygen. It has oxygen and water vapor. I gave you the pressure of the water vapor. You have to subtract it because the pressure I want right here is just the pressure of O2, not O2 and something else. Does that make sense? All right. Let us continue on our journey. Just a couple of little things to wrap up this chapter. Okay, you learned in Chem 1 something called the kinetic molecular theory, which is just some characteristics of an ideal gas, a definition or two here. Okay, in an ideal gas, ladies and gentlemen, the volume of any gas particle is very close to zero. Okay, it's not zero, but it's very small. Okay. We talked about how all gases exert pressure. Do you remember how I wanted you to visualize pressure of a gas? Do you remember? Hits on the side of the container. Ask yourself, is what's happening going to cause more hits or less hits? That's a way to predict what's happening to the pressure of that gas. Collisions. Okay? An ideal gas means gas particles exert no forces on each other. Do real gases exert forces on each other? Yes. Okay, we're talking ideal gas here. And here's a definition which we've already talked about. Remember that the definition of temperature is the average kinetic energy. Kinetic energy is the energy of what? Motion, movement. So visualize in your mind as temperature of a gas goes up, their motion increases. Now, this is the last little bit that we're going to talk about today. Diffusion, effusion. We are only going to discuss this in a conceptual way. We're not going to calculate anything, which means for those of you that have the slides, you may cross out the following slide that comes after this one, because it has you calculating something, and we're not doing that. We are only going to discuss diffusion and effusion conceptually. And I'm going to give you the world's most ridiculous analogy that will help you never ever forget what diffusion and effusion mean. Okay? These definitions are pretty fancy. I'm going to give you some sort of straightforward definitions. Diffusion means movement of one gas through other gases. That's what diffusion means. Movement of one gas through other gases. Perfect real-life example. I will tell you, this hallway that my classroom is on used to be, for years and years and years, used to be the hallway where the freshman lockers were. Okay? Only in the last couple of years has Oakton started doing this thing where you keep the same locker for all 4 years. It used to be you got a new locker, a different locker every year, and the freshman lockers were always on this hallway. What a joy for me to be on the freshman hallway. Okay? And I apologize to the young men in this class, but I'm going to throw boys under the bus here. On this freshman hallway, it was always the boys, not the girls, always the boys, who went a little crazy with something called Axe body spray. Okay? Now, I'm not trying to throw this, I'm not trying to, make this out to be a bad product. I'm sure it's a wonderful product. In small doses. Okay, in moderation is right. A little just, you're good. But no. There was always this pack of boys out in this hallway that did not believe in the one spritz. They were way too much. Okay? And I don't care if this kid, or kids, plural, was down at the entire other end of the hallway. It did not take long for this cloud of Axe body spray gas to diffuse down the hallway, through my door, into this room, over to my desk where I'm smelling it, and then I get very salty and I get upset. Okay? That's a word I use. I get very salty. I get salty. I don't like it. Okay? So, that is a perfect example of one gas moving through other gases. Okay? That's diffusion. Now I'm going to give you the world's most ridiculous analogy. I want you to imagine that this room is filled wall to wall, floor to ceiling, with sumo wrestlers. Okay? They are crammed in here. It's like a cocktail party of sumo wrestlers, body to body. It's tight in here. Okay? And you are at the back door of my classroom, and your objective is to move from that door to the front door as fast as you can. Okay? I want you just to imagine the mechanics of that. You're trying to move these 400 to 500 pound bodies aside so you can slither past. Okay? I want you to imagine a second situation, that this room is filled wall to wall, floor to ceiling with cute little bunny rabbits. Oh. Okay? It's just as full, but it's now filled with bunny rabbits. And again, your objective is to move from the back door to the front door. In which situation will you be able to move faster? The bunnies. Okay?
just like 5, there would be like a couple of them stacked 5. That would be so cool.
Well, the point is, it is much easier to move even a tower of bunnies aside than it is to move a sumo wrestler aside. Let's bring this back to chemistry. I want you to look at our noble gases, group 18. Tell me, could a gas diffuse, let's use extremes. We've got a room filled with helium, and then let's go all the way down to the bottom. We've got a room filled with radon, which is poisonous, so hopefully we're not breathing too deeply. All right? Is it easier for a gas to diffuse through helium or radon? Why?
Because it's lighter.
It's smaller. It has a smaller molar mass. Ladies and gentlemen, diffusion and effusion, for that matter, are tied to molar mass. The smaller the molar mass, the faster your rate of diffusion. You can move faster through a room of bunnies than a room of sumo wrestlers. Let's talk effusion. All right? What does the prefix E or X mean in a word? Out of. Okay? Effusion, ladies and gentlemen, is passage of a gas through a small opening. And you know what? I'm going to take this down that 8-year-old boy humor road. I know some of you are thinking it. You're thinking about farts. Yep. Is that not passage of a gas through a small opening? Yes, it is, ladies and gentlemen. That is that's an example of effusion. But let me give you a not so gross example. All right, you know how much I love balloons. But if you have any balloon, the normal kind, the silvery mylar kind, or even like a beach ball that's inflated, anything that's inflated, if you put those things aside for like days, weeks, months, they deflate over time. Why are they deflating? You didn't cut a hole in them. Why does a balloon deflate slowly over time?
Effusion.
Okay, effusion, correct, but tell me how that's happening. What holes? What hole is it effusing out of? Cole?
Is it that the molecules escape through like tiny holes?
You got it. They are called micropores, ladies and gentlemen, meaning really small holes. Any material, you know, a rubber balloon, mylar, plastic, vinyl, anything like that has what are called micropores. And the gases escape slowly. Let's go back to our ridiculous analogy, although I'm going to change it a little bit. Okay, the room is still packed with sumo wrestlers. We're still at the cocktail party. All right? But I'm going to go out in the hallway and I'm going to pull the fire alarm. Which, by the way, for a false alarm is a felony, people. Not a misdemeanor. Felony. Yeah.
It's pretty crazy.
To pull a fire alarm when there is no fire is a felony.
So you can like go to prison.
You got it.
Wow.
Yeah.
Should not pull a fire alarm if you smell
What if something is burning?
something smells like but it was nothing.
Well, you can plead your case in court.
They might get
Okay?
I think the general rule is unless you see the fire, don't lose it alone.
Good call. Now, you're not in the room anymore, but the sumo wrestlers are in here. I pulled the fire alarm. They have got to evacuate through that door as fast as possible. Let's just look at the area of the door here. Let's imagine.
How did they go in?
They got in. You know, maybe we have to like grease the doorway and kind of shove them a little bit. Okay? Which room could evacuate faster? A room of sumo wrestlers or a room of bunny rabbits? Bunny rabbits! Especially if I put like a wolf in the back corner. Yeah, they get out. Alright, so tell me, Let's bring it back to a chemistry example. I'll use the same extremes. I have a balloon with helium, and I have a balloon with radon, which would be stupid because radon is so heavy it would be a balloon on the floor. Which balloon would deflate faster? Why? It has a smaller molar mass. It works the same for effusion and diffusion. As the molar mass gets smaller, the speed of effusion and diffusion speeds up. Okay? So, again, we are not going through this. All these equations are showing is that relationship, that inverse relationship between molar mass and speed. But I'm not going to have you calculate anything, so guess what? That's it for Chapter 5. So, ladies and gentlemen, remember that Chapters 5 and 13 are going to be put together, and you might think gas laws, equilibrium, do they really go together? Actually, they go together very, very well. So let's just start off by, kind of refreshing our memories about what equilibrium means, okay? Some of what is in this chapter will be review. I would imagine most of it is going to be new, but it is not difficult, okay? But you should all have been exposed to at least the definition of equilibrium, all right? 99.999% of chemical reactions out there are reversible. Meaning, we're going in the forward direction to start with. Reactants to products. And when those products start to build up and build up and build up, eventually, the reaction can start to move in the reverse direction, where products are now going back and forming reactants. Let me give you an example of a reaction that is, for the most part, not reversible. Think about if you were to drop a match into the gas tank of a car. Boom! Okay? Do you know what the products are of any combustion reaction of a hydrocarbon? Tell me, James. Nope. Not oxygen. Water and carbon dioxide. Okay? When you blow up a car, which you're not, you get CO2 and water. Is that CO2 and water going to recombine to form the gasoline again and oxygen gas? Probably not. Okay? But most reactions are reversible. And when the forward and reverse rates are moving at the same speed, that is by definition equilibrium. Okay? Forward and reverse rates are equal. For those of you that have the slides, put a star next to this statement. It's very important. It addresses a misconception that a lot of people have about equilibrium. A lot of people think equilibrium means reactants and products are equal in amount. And that is false. Equilibrium means the rates are equal. It has nothing to do with amounts or concentrations of your reactants and products. It just means the speeds are equal. Okay? And this is a way to look at that graphically. Now, one of the first things that you will be asked to do in your problem set and a lot on multiple choice is something that is so easy. You'll be given a reaction and you will be asked to write what is called an equilibrium constant expression. Ladies and gentlemen, if you ever see the word expression, that means there's no calculating involved. Okay? Expression means we're not crunching any numbers yet. First of all, an equilibrium constant is a capital K. A lowercase k in chemistry means something else. So make sure you recognize it as a capitalized K. And since it's a constant, does anybody know why it gets the letter K and not the letter C for constant? C is carbon. Well, that's true. Kelvin. K is Kelvin. For a unit, yes. It is because the scientists that were really coming up with a lot of this equilibrium stuff were German. The word constant in German starts with a K. Okay? When you get to decide something, when you're the one that discovers things, you can name them, label them, whatever you want. Okay? Now, tell me, what do brackets mean? Molarities. If I ask you to write an equilibrium expression, you take your products, the molarities of your products, divided by the molarities of your reactants. Please notice that these things are being multiplied, not added, like they are in the equation. And if there are coefficients, those coefficients become exponents. Okay? There's no numbers. There's no calculating. Right? I also want to call your attention to the fact that if you ever see the equilibrium constant written like this, a capital K with a subscript C, okay? These are the same thing. K and KC mean the same thing. Anybody want to guess what C stands for? It's not constant. Not Celsius. Concentration. Molarities are concentrations. Okay? So do not be confused. These things mean the same thing. And here's an example of an equilibrium expression. And guys, you will have multiple choice questions as simple as, here is an equation. Which one of the following, A, B, C, or D, is the correct equilibrium expression? And there it is. Yes, sir? We'll get to that. All right? I want you to notice the state of matter of everything in this equation. What does G mean? Gas. Think back to Chem 1. What two states of matter, gas is one of them, what's the other state of matter that it is you can include in an expression? Do you remember? It's gases and, nope, aqueous. Gases and aqueous you may include. So that means what can you not include? Solids and liquids. So, for example, let's say that NO2 wasn't a gas, but was a liquid. That means this just wouldn't be here at all. And what if I make another change? What if this H2O wasn't gaseous H2O, it was solid? What, if I had this situation, what would be in the numerator? 1. I'm glad you didn't say 0. The expression would be K equals 1 over this to the 4th, O2 to the 7th. Okay? Okay, yes?
And you would do that instead of like NH3 to nitrogen 4.
I mean, technically that would be correct, but just write it like that. Alright. Now, for For the moment, I don't even want you to read what's at the top of this slide. What I want you to look at, I want you to move your eyes from this line right here. This is the same reaction I had on the previous slide. This line down to this line. What happened? It flipped. The two things that were my reactants are now my products. Okay, guys, on multiple choice again, and in your problem set, you're going to have questions that'll say, if the equilibrium constant for this first reaction equals the number 10, what is the equilibrium constant equal to when you flip it? Okay, glad nobody said negative 10. Think about it. The equilibrium expression comes from dividing products over reactants. Let's actually put in numbers there. How about 10 divided by 1? If your reactants and products have switched places, isn't that what the new K would be equal to? What do you call something when you flip it, flip a fraction? The reciprocal. Right? It's a reciprocal. Okay. And guys, on a multiple choice situation, I would use nice, easy numbers like this. Okay? I'm not going to make this K equal to something crazy and expect you to do the mental math. I'm going to use nice, easy numbers like this. It's a reciprocal. Okay? Again, don't even worry about what's up here. Tell me what has happened to go from here to there. It's been doubled. It's been multiplied by 2. Right? Multiplied by 2. Multiplied by 2. Okay? What do you think the new K value would be? Not 20. Your old K value raised to the power of whatever you multiplied by. 100. Okay. What if I did this? Are you ready? And this was then 12, 21, 12, 18. 10 to the, which is, there you go. Okay. All right. What if I did this? Let me rewrite it down here. Okay? From the original down to here, what have I done? From the original, I flipped it and doubled it. Okay? I flipped it and I doubled it. Well, first of all, what would you do? What do you do when you flip something? Okay? What do you do if you double something? Raise it to that power. That is what you would do. Okay? So that would be 1 over 100. Okay? Be aware that you're going to see questions, not only in your problem set, but also on multiple choice, where two things are happening. Like it's been flipped and multiplied by some number. Right? Now, we're going to take a little walk down history lane here for a second. Okay. I want you all to be aware that on the AP exam, particularly in multiple choice, there are questions that I call life questions. They're questions that are not in your textbook. They're not in your Princeton review book. They're not something I'm going to teach you. They're just things you either know it or you don't. For example, last year in multiple choice there was a question that asked, what acid is responsible for acid rain? Do you know? What acid by name is the acid that's in acid rain? It is sulfuric. I'm not teaching you that. That's either something you just know or you don't. Okay, now you know that one. Here's another one that comes up a lot. How are you supposed to study for that? I don't know. You're not. Yeah, it's a Jeopardy. It's like Jeopardy questions. Here is why I'm bringing that up. Okay, what is on this slide has actually nothing to do with what I'm about to talk about. This is just this reaction that is on this chart. Let me just rewrite it for you. Has a name that you should know. What kind of reaction is that? Synthesis. This is the synthesis of what? Ammonia. Okay? Folks, this reaction has a name. It is called the Haber process. You need to know that. This is just one of these life chemistry questions that I am actually teaching you. Okay? And let's take a stroll down history lane. This is named after a person, Dr. Haber. Not Dr. Process. Someone said that in the last class. Dr. Process? No. Okay. Dr. Haber was alive in like the teens, 20s, 30s, 40s, 1920, 1930. Okay, he was a German citizen. And he, when Germany went into World War I, okay, he joined the army and was not like a soldier on the front lines. He served the army in a scientific capacity. They asked him to come up with a way to synthesize something, basically gases that could be used as military weapons, right? And he created, it's not that, ammonia didn't exist before this time, but there wasn't a rapid way to synthesize ammonia, and he came up with the process to mass manufacture little capsules that when you launch them or fire them over, a field into enemy territory, when they would open, it would release all this gas and kill people. Okay? And he was successful with that. Okay? So, time goes on, time goes on, time goes on. This is about to get really depressing. Sorry. Alright? We now enter the late 1930s, early 1940s. What's happening in Germany at this time? Nazis, Hitler, concentration camps. Okay? Concentration camps needed a way. You've probably heard about them. They were called death chambers. They needed a space and a chemical to put into that space to kill mass amounts of people fairly rapidly. And this is one of the ones that they used. Now, this is ultimately probably one of the saddest stories ever, because Dr. Haber was Jewish. He was able to get out of Germany before he could have been put into a concentration camp. But imagine, his life is like the saddest life ever, okay? Imagine, if you will, that you've served your country in one capacity, and then later on in your life, your greatest achievement is responsible for the death of millions of people, of your own people, okay? It's a really, I've read about this poor man who, I believe, moved to England, was never able to return to his Germany again. And I don't know that he would have wanted to anyway, but, I mean, it's a horrible story. But I bet you won't forget it. Okay? Yes, Ed.
So, is it good for ammonia or is it for any compound?
It is for ammonia. The synthesis of ammonia is called the Haber process. Now, does this have anything to do with what's on this slide? No, not really. Okay? The only reason I brought that up is because this reaction is on this slide. But here is what's important to learn here. This first statement in orange is the big one. See you later. Okay? You can only change the value of an equilibrium constant if you change the temperature. Austin, are you alive? Okay, good. I have to check. He could be dead. I have to check. It happened to a teacher in Texas. She thought he was dead, or asleep, and he was dead.
Oh my god.
Are you serious?
Yes.
Where did he die from?
Aneurysm, I think. Anyway, people, the point is, you can change anything you want. You could change the pressure in the room. You could change the volume of the container. You could change the amount of reactants, amount of products. You could mess with this equation in any way that you want, except for changing the temperature, and your K value would come out to be the same thing every single time. Temperature is the only thing that can change it. Okay? Now, we saw earlier Kc. What did the C stand for? Concentration. Well, here's a different one. What do you think P stands for? Pressure. Ladies and gentlemen, you can set up an expression just like a Kc expression, but instead of molarities, notice the brackets are gone, you can sub in partial pressures. It's still products over reactants. Now let's just recap for a second. What were the two states of matter that it was okay to include in a Kc expression? Gases and aqueous. If you're using pressures, think about that for a second. What do you think it makes sense to include?
Yes.
Gases only. Okay? It just so happens in this reaction everything is a gas. If I ask you to write a Kp expression and, this one was a solid, it just wouldn't be there. Because we don't talk about pressure of solids. Okay? I want you to completely cross out this slide. Get rid of it. It's gone. And I'm moving on. This is the last thing we're going to talk about. Ladies and gentlemen, what does the word heterogeneous mean to you? And I'm not saying heterogeneous mixture, just heterogeneous. What does it mean? Different. Okay? Ladies and gentlemen, if you ever see the term heterogeneous equilibrium, all that means is that everything in your chemical equation is not the same state of matter. That's all that means. If this were solid, 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 what do you think I would call it? Homogeneous equilibrium. Okay. And just to make sure that you're all paying attention, This is the equilibrium expression for this reaction. Why is it so small and short? There's three things here. Ah, we leave out solids. Good. Just making sure you're paying attention. And folks, that is where we're stopping.